everyone, I'm Teacher Teresa. So today I'm going to go through the last type of structure with you. Okay, so far you have watched videos about the structure for ionic compound and for covalent compound. So today we're going to go through the last type of substance, the metal itself. So in grade 9 you have learned there's bonding in metals. It's called the metallic bond. It's the electrostatic force between the metallic ions and also the sea of delocalized electrons. So if we're going to describe the structure for metals, then we're not going to have the diagram that only shows one layer of metals, but we're going to have different layers of metals stacked together. So here I'm going to attach a 3D photos demonstrating the metallic structure. Okay, so you can see those positive ions represent metal cation, and you will be able to see some small circles with negative charge. They are representing the delocalized electrons. One thing that you can notice on this diagram is that when we draw the delocalized electrons, their position are not fixed. Okay, actually they are quite random, so you can find one here, and find another one here. So unlike the giant ionic structure, we draw the cation and anion in fixed position. So for giant metallic structure, we have delocalized electrons that can move among those cations. So we just draw them in random places. For students taking the AC or IFI courses, you will be required to draw these diagrams in the final exam. So make sure, besides the drawing of the cations and electrons, you need to make sure you also label them. So this represents the metal cation. In the small circle, usually we put negative charge in that. That represents the delocalized electrons. Okay, and the forces, attractive force between the metal cation and the sea of delocalized electrons are called metallic bond. That we can say delocalized electron or mobile electron. Okay, so now let's move on to take a look at the properties of metals. So the first one, physical states. So metals are usually lustrous or shiny. When they are polished or freshly cut off. Okay, because some metals are quite reactive, they regularly react with air, oxygen in the air, and then it turns into a dull surface. But most of them, when you freshly cut it, you will see the shiny surface. And also, most of them are silvery white in color. But we have a few exceptional cases. So for gold, it's golden yellow, and also for copper, it's reddish brown in color. Okay, except the appearance, we also need to talk about the physical states for metals. So most metals, they are solid at room temperature. And again, there are one exceptional case, which is mercury. So mercury is a liquid at room temperature, and in the old days, mercury has been used in the thermometer, and its volume can easily expand when the temperature increases. Okay, so that's the first part, physical states. And then let's take a look at the strength and hardness for metals. Okay, I don't know if you still remember, your teachers have done some demonstration with group 1 metals in grade 9. Okay, so we took potassium or sodium from the paraffin oil, and then we can cut it using the knife. So for group 1 metal, they are generally speaking a bit soft compared to other metals. But all other metals, you won't be able to use a knife to cut them. So we say, except from group 1 metal, all other metals, they are usually strong and hard. Okay, and why they are strong and hard? Now you understand the giant metallic structure, so we can use the structure to explain the property. So metallic metals, they have metallic bonds, and the metallic atoms, they are held together by strong metallic bonds, and they are tightly packed in a giant lattice structure, so they are very strong and hard. Okay, then move on to point 3, the density. Okay, again, I need you to recall your memory about the experiment and reactions we did in grade 9. Okay, so we learned some reaction between metals and water. So the 3 examples we have seen potassium, sodium, and calcium. Okay, so potassium and sodium, or in more general cases, group 1 metals, they are lighter than water, so they would be able to float on water surface. But the rest of the metals, or metals in general, they have a high density, and they are going to sink down to the bottom of the beaker. Okay, but again, we have some exceptional case. Sodium and potassium. Okay, so those are the ones you have seen before in grade 9. Okay, and again, the reason is about its structure. So the atoms of the metals, they are held together by the strong metallic bond. And they are packed in a small volume. So with a small volume, then they have a higher density. Okay, so that's 4.3. Next one, number 4, melting point and boiling point. So we all have a common sense that metals should have a relatively high melting point and boiling point, because we will not be able to easily melt our cooking pan or our spoons or forks and knives that we are using. Okay, and we can draw a conclusion. Metals usually have high melting point and boiling point. Again, we need to be able to explain that with reference to its structure. So this is because metallic ions and the delocalized electrons are held together by strong metallic bond. So if we want to separate the ions or the delocalized electron, we need to apply a lot of energy to break the bond. So that's why it has a very high melting point and boiling point. Okay, and then point 5, electrical conductivities. Okay, again, we all know all metals are good electrical conductor. Okay, so in the previous part, we have learned in order to be able to conduct electricity, we must have charged particles to carry the current. So in the case of metals, it's the mobile electron or the delocalized electron that carry the charge and then to conduct electricity. Pay attention here, we're not talking about the movement of the metal cation. Okay, remember, it's not the metal cation that move to conduct the electricity. It will only be the mobile electrons move to conduct the electricity. Okay, and in the table, we can compare the two things that can conduct electricity. So for metal, it would be able to conduct electricity at room state, room temperature, room pressure. That's because it contains mobile or delocalized electron. Okay, and remember, we never say free electrons or free ions, and we don't have delocalized ion as well. So again, metal cations in a giant metallic structure will not move when it's connected to a electrical source. Okay, and then for the case of ionic compound, it can also conduct electricity, but it can only conduct electricity when in molten states. That means it's turned into liquid, or in aqueous solution. That means it has been dissolved in water. So in those two cases, it contains mobile ions, so that it can conduct electricity. So for the case of ionic compound, remember they don't have mobile electrons. It only has mobile ions that can move to conduct electricity. Okay, and then move on to number 6, thermal conductivity. I believe we all have some experience that metals are good heat conductor. Okay, so that's why we use metal to make the cooking pans, and in some cases, if we put a spoon in a very hot soup for some time, the spoon going to become the metal spoon going to get very hot after 1 or 2 minutes. Okay, so we say all metals, they are good conductors of heat. Okay, and again, we need to be able to expand it from the point of view of a structure. So why it can conduct heat? So in the diagram, this represents the heat source, okay, like the fire. Okay, so the heat source can transfer the thermal energy to the closest electrons on the metal, and then those electrons, after getting the thermal energy, it would convert it into kinetic energy. Okay, so if it has more kinetic energy, that means it can move faster. And then those electrons, because they are now moving quicker, then they would collide more frequently with the adjacent electrons. Okay, those electrons sit next to them. And then they will pass their kinetic energy to the next electron. And now this electron have gained extra energy. And now this electron will move faster. And then this electron would collide with the next electron and then pass the energy. Okay, so that's how metals conduct heat. So by the collision of electrons from the heat source. So it's always from the hot side to the cool side by collision of electron. Okay, again, it's nothing to do with a metal cation. It's all about the movement of the electron. Okay, so we can highlight that part. Okay, and one more misconception that some students might have is that they think, okay, so my electron near the heat source, they gain energy, and then they bring those energy all along to the other side of the metal. That's not the case. Okay, it's not 1 or 2 electrons gaining the energy and bring it to the other end, but they collide with the next electron and then pass along the metal. Okay. Later, we will have one checkpoint about the thermal conductivity of the metal, and then I will use another example to further explain this. Alright, then let's move on to number 7, solubility. Okay, so most metals, they are insoluble in water and non-aqueous solvent. So non-aqueous solvent, for example, oil. Okay. However, some metals, like the ones we have learned in grade 9, sodium, potassium, and calcium, they can react with water. So for all the examples of metals that can react with water, we will learn in Unit 11. Alright, then move on to number 8, malleability and ductility. So these two words might be new to you. Okay, they usually come together, they have similar meaning, but they have some differences. Okay, so I want to show you the video that demonstrates these two properties of metals first. The first part of the video demonstrates the malleability of metals. You can see we can use a hammer to change the hot iron's shape, so we can make the tip very sharp and pointed, and then we can make the head a flat surface. Then we can take a look at the second part. It demonstrates the ductility of the metal. We can use a machine to stretch the two ends of the wire, and then originally we have a thick wire, but after some time we can stretch it into a very thin one. We can compare the final product, it's much thinner. Okay, so let me use a blue tag to demonstrate the difference between malleability and ductility again. So if we are compressing the blue tag, we're applying a compressive force, then we're and make it into a flat pieces, then that's demonstrating the malleability of the metals. But if we are, for example, pouring the two ends of the blue tag and make it become thinner, then we're demonstrating the ductility of metals. We're applying a tensile force, so pouring the two ends to make it thinner. Okay, so that's a difference. Okay, let's summarize on the notes. So all metals, they are malleable. So malleable and ductile, they are adjectives. And malleability and ductility, they are nouns. Okay, so all metals, they are both malleable. Okay, can be rolled into sheets, like applying a compressive force, and also they are ductile. Okay, so they can be pulled into wires. So we're applying a tensile forces. Okay, so why is that? Why metal have not such special properties? Again, we need to look at its structure. So the metal ions packed regularly in layers and are held together by metallic bonds. So that's what we usually draw for metallic structure. So when we apply a strong force to metal, then we are going to press one of the layer to the side. Okay, so you can see this layer has been pushed to the right hand side. Although this layer has been moved to a new places, because the metallic bonds are non-directional, so we can still have a lot of electrons surrounding these layers of metal cation. And those electrons can still hold this layer of metal cations in space. So what I'm talking is when we apply a force, even though the metal cations have been moved to a new position, the metallic bonds are not broken. Okay, so they can still held together without changing the structure. Like the shape has changed, but we didn't break them apart. So that's what malleability and ductility mean. Okay, so here, when a strong force is applied on a metal, the layers of metal ions can slide over one another. And because metallic bonds are non-directional, the metal ions still be held by the metallic bonds when the metal ions are settled in a new position. Okay, so during this process, we didn't break the metallic bonds. The metallic bonds just reformed instantaneously, so they can still hold the structure like before. Okay, so these are the 8 properties you need to remember for metals. So you may now pause the video and quickly attempt the checkpoint questions. Okay, so let's take a look. Number 1, most metals have high melting point and boiling point because. Okay, so again, when we're comparing the property, we need to look at the structure and the bondings in that substance. So for metals, they have giant metallic structure and they have metallic bonds. Okay, and metallic bonds are very strong and they are of the similar strength of covalent bond and ionic bond. Okay, so it's not metallic bonds are stronger than those two, but they are of similar strength. So the most appropriate answer for this one should be C. Okay, they are usually strong and not easily broken. Okay, and then number 2. Which of the following explanations about the thermal conductivity of metal is correct? Right, so remember, when we talk about the thermal conductivity of metals, we're talking about the movement of electrons, the mobile or delocalized electron. The metal cations will not move, so we can quickly cross out A and D. Okay, and then for B and C, what's the difference between B and C? Okay, B is saying free electrons near the energy source gain energy. They run throughout the metal and transfer energy to all parts of the metal. Okay, so first of all, one thing I want you to modify on your notes is that we never use free electron. Okay, it should be mobile electron. Okay, and then what's the difference between B and C? So B is saying if that's our heat source, then B is saying one of the person grab a bucket, okay, and then this person going to get the water and then go to the fire and then goes back to collect water again and then do the thing again, right? That's what the scenario in B is describing. So when we get closer to the heat source, one of the electron gain energy and then going back. But for the case of C, again we have a heat source, and then in the case of C we have a lot of people lined up, right? And what they are going to do is one of the person going to grab the water, the bucket with the water, and then he going to pass to the next person, and then the next person going to pass to the person near the fire, and then the first person going to grab another bucket with water to do it. Okay, so it's not one of the person comes in and goes back. It's not the person run throughout the way. Okay, so in the case of metal, okay, B is representing that the electron near the heat source that going to run throughout the metal. But for the case of C, it's talking about the electron that near the source get the energy and then pass to the next electron and then pass to the next electron. Okay, so you can clearly see C is a scenario we just described in the previous page. Okay, so the electron get the energy, heat the next electron or collide with the next electron, and then heat the next electron to pass through the energy. So again, the most appropriate answer for this one should be C. Now let's do a summary of this unit. So in this unit, you have learned 4 structures in total. And how do we decide what kind of structure a substance has? Okay, we need to look at its composition. So if the substance contains metal only, then it can only have giant metallic structure. But if the substance contains non-metals only, then you need to consider 2 cases. If it's one of the special case that you have learned for giant covalent structure, graphite, silicon, silicon dioxide, diamond, then it has giant covalent structure. But you can assume the rest of the non-metals, they would adopt simple molecular structure. Okay, and then if you have a metal that combine with non-metal, then it would have giant ionic structure. So here we have 3 examples, and then you can pause the video here and try to solve what kind of structure they have. Okay, so let's zoom in to take a look. So for the first one, carbon dioxide, we have carbon and oxygen. Both of them are non-metal, so we need to look at this part. Okay, they have non-metals only, and then it doesn't belong to any 4 of the special case we have learned: silicon dioxide, silicon, graphite, or diamond. So it should have a simple molecular structure for this. Okay, so non-metal. And then it has small molecules. Then it should have simple molecular structure. Okay, then the next example, sodium oxide. Okay, sodium is a metal, oxygen is a non-metal, so that's metal plus non-metal. So it would adopt a giant ionic structure. Sorry. Okay, and lastly, we have magnesium. Magnesium is a metal, so it would have giant metallic structure. Right, so that's how we decide what kind of structure it has. Okay, on the next page is summarize the structure and the bonding in each structure for different compounds and elements, and also it summarizes the properties for different structures. So these rows is summarize the bonding, so I'm not going to go through them with you. I want you to revise on your own. But now I want you to focus on the properties. Okay, why the properties are important? Because sometimes when we are given an unknown substance, we can use a property to predict what kind of structure it has. Okay, we need to find the unique feature for that substance, and then we can try to predict what kind of structure it has. For example, if I'm trying to look for two students in the whole grade, for example, I come to ask you, okay, I'm looking for, let's say, Adrian and Fergus. Can anyone tell me what's the difference between them? How do I recognize who is Adrian, who is Fergus? Right, then you might tell me, okay, one is wearing glasses, if the other one doesn't. One with long hair, the other one with short hair. One is wearing a jacket, the other one doesn't. So you would like to tell me some unique information about that student so I can recognize him. Okay, so similar principle going to apply here. We're trying to find out some unique properties for that specific structure. So if we find out an unknown substance have that specific structure, then we can draw a conclusion. Okay, this substance should have this structure. Okay, so let's begin with the first two rows, the physical state and melting point and boiling point. First of all, for the physical state row, you can see most of them would adopt solid state. The only exceptional case is for simple molecular structure. It might exist as a liquid or a gas. Okay, and that's to do with a weak van der Waals forces between molecules, so they can be easily overcome and be separated and become liquid or gas. So if you are given an unknown substance that exists as liquid or gas, okay, and then you can draw a conclusion it's probably simple molecular structure substance. Of course, we need to consider the exceptional case. We have mercury, that's a metal that exists as liquid state at room temperature. Okay, so similarly, the melting point and boiling point. So you can see giant ionic structure, giant covalent structure, giant metallic structure. Okay, if they have a giant structure, then they would have a high melting point and boiling point. So again, I want you to highlight this part. Okay, if you are given a substance that has a low melting point, then you can conclude it probably has a simple molecular structure. Okay, the next row, hardness. Okay, again, we're doing comparison to find out the unique property. So again, I want you to highlight this one. So for the simple molecular structure, it's usually soft. Again, that's to do with a weak van der Waals forces between molecules. And then for the rest three giant structure, because they either have strong ionic bond, strong covalent bond, or strong metallic bond, so it requires a lot of energy to separate them. So they are very hard in general. Okay, and then the solubility. Solubility we will discuss in later units, so I'm not going to bother too much with that row. And then lastly, electrical conductivity. Okay, so this one is a very useful property we can use to predict the structure. Okay, so first of all, you need to remember for covalent compound, they do not conduct electricity in general. Of course, we got one exceptional case, that's graphite. But for the rest of the covalent substance, they do not conduct electricity in any circumstances. Okay, and then if we take a look at the giant metallic structure, it can conduct electricity at standard state. But for the case of giant ionic structure, it can only conduct electricity in molten or liquid states or aqueous states only. Okay, so those highlighted part are their kind of unit property that can help you to identify the substance. Finally, let's try to apply what we have learned in this unit and attempt some questions together. Again, you may pause the video here and come back to listen for explanation. Okay, so for number 1, in terms of bonding and structure, compare the melting point of water and sodium chloride. Okay, so remember in this unit, whenever you are asked to compare a property for a given substance, you must follow this pattern. You must first name the structure, and then you must describe the bonding, and then you need to compare how much energy is needed to overcome the bonding or separate the molecules. So the last part, you're going to relate the properties to the energy required to do so. Okay, so let's see how it applies to answer questions. The first one, here we are comparing water and sodium chloride's melting point. So remember, follow the pattern. We're going to name the structure first. So water, H2O, is made up of two nonmetals, hydrogen and oxygen. So it's a covalent compound, and it should have simple molecular structure. So we name the structure first. Okay, and then we're going to describe the bonding in water. So although atoms in water molecules are held together by strong covalent bond, the water molecules are attracted to each other by weak van der Waals forces. Okay, and then to do comparison, we're going to describe the structure and the bonding for sodium chloride as well. Sodium chloride, NaCl, so it's combining a metal with non-metal, so it would adopt the giant ionic structure. Okay, and ions are held together by strong ionic bond. Okay, so we've done with these two parts. We have named the structure and we have described the bonding. Now to do comparison, we need to compare the amount of energy needed to melt the two substances. So during melting, as much less amount of energy is required to break the weak van der Waals forces between molecules compared to breaking the strong ionic bond between ions in sodium chloride. Water has lower melting point. Okay, so here remember, because you are new to chemistry, so we want you to develop some good habits. Whenever you are describing the bonding, we want you to not only name the bond, but also use the correct term to describe the particles involved. So for example, we're saying atoms in water molecule that's bonded by covalent bond. Okay, and we're not just saying water molecules has covalent bond and van der Waals forces. Okay, remember you need to name the particles involved. So covalent bond between atoms, weak van der Waals forces between molecules, and giant ionic bond between ions. Right, so when we're comparing the amount of energies needed, we say less energy required to break the weak van der Waals forces between molecule, okay, not required to break the van der Waals forces between atoms, okay, name the particles properly, okay, and then is compared to breaking the strong ionic bonds between ions, not between atoms in sodium chloride, okay, so pay attention to the name of the particles, they are important. Now let's move on to question 2. You're given 3 diagrams, so you need to consider the following structures. And for part A, you are asked to name 3 substances which have the same structure as A, B, and C. Okay, so remember, because you are asked to name the substance, so writing the formula will not count. Okay, so for A, you can see there are small molecules in the structure, and you can see within each molecule, you have 2 particles stick together. So that means this diagram is representing a diatomic molecules. Okay, so there are many possible answers for structure A, and there are some common examples that you have learned in grade 9. So for example, hydrogen gas, it exists as diatomic molecules. Okay, and there are many other gases that would exist as diatomic, such as nitrogen and oxygen. Okay, and also some other halogens, they will exist as diatomic molecules. So for example, we can have iodine and chlorine that exist the same structure as shown in structure A. Okay, so pay attention because you are asked to name it. So if you write H2 or O2, it will not be counted. Okay, don't write formulas when you are asked to name the substance. Okay, let's move on to B. So for B, you can see it forms a lattice structure, and then you can see the ions, they take alternative positions. So that matches with the structure that you have learned for sodium chloride. So you can write down your answer for that one. Okay, then move on to C. Okay, so for C, you can see again it has a giant structure, and then you will see it forms a tetrahedral shape for each small unit. So that's the structure that you have learned for diamond or silicon. Okay, so that's for part A. And then part B, name the type of bonding between particles in A, B, and C. Again, because you are new to this unit, so while you describe the bonding, I would like you to also name the particles involved. Okay, so for structure A, we have simple molecular structure. So you should name, first of all, they have strong covalent bond between atoms, and also you have van der Waals forces between molecules. Okay, so remember, name the particles involved as well. Right, then move on to B. Because B is representing the giant ionic structure, so it should only have ionic bond between ions. And then lastly, it has a giant covalent structure, so it should contain covalent bonds between atoms. Okay, and then let's move on to the last part, part C. In terms of the forces between particles, explain why there is a large difference in melting point between A and B, and then in A and C. Okay, remember, in each case, state which of the 2 solids is expected to have the higher melting point. Remember, just now we mentioned when we are asked to compare the properties of given substance, we need to follow the pattern, which is we name the structure first, and then we describe the bonding, and finally we compare the energy to do that. Okay, so let's use that pattern, or I copy it here to remind you that you need to follow this pattern to answer the question. Okay, so let's take a look. A and B. Okay, we're comparing the melting point. So just now we saw the diagram. A has simple molecular structure, B has giant ionic structure. So we're going to begin with that part. Right, so A has simple molecular structure. Okay, and then the molecules are held together by weak van der Waals forces. Okay, so remember, after name the structure, you need to describe the bonding, and while describe the bonding, you need to name the particles involved. Okay, so the molecules are held together by weak van der Waals, not atoms. Okay, and that's for A. Then to do comparison, we need to also describe the structure and bonding in B. So B has giant ionic structure. Ions are held together by strong ionic bond. Okay, so we finished describing this bonding in B as well. Then finally, we need to do comparison between A and B, how much energy is needed. Okay, so we're going to say during melting, more energy is required to break the strong ionic bond in B compared to break the weak van der Waals forces in A. Okay, therefore, B has higher melting point than A. Okay, so remember, after compare the energy required, you need to draw the conclusion. That's asked by the question. You need to compare the compare the melting point between the two substances. Okay, so that's for the first case. We are comparing A and B. Then for A and C, can you do the same? So let's try it together. So again, we are going to comment on the structure. So for A, it's going to be the same. So we can select that and then copy to here. Okay, A has simple molecular structure. The molecules are held together by weak van der Waals forces. Right, and then we need to do the same for C. Okay, so C has giant covalent structure. Atoms are held together by strong covalent bonds. Okay, so again, we describe this, name the structure and then we describe the bonding. Then lastly, we need to compare the energy required. So during melting, more energy is required to break the strong covalent bond in C compared to break the weak van der Waals forces, capital W, in A. Therefore, C has a higher melting point. Okay. So remember, we always follow this pattern. We're going to name the structure, then compare this, then describe the bonding, finally compare the energy required. Then don't forget, lastly, you have to state your conclusion, which one has a higher melting point or boiling point. And it's very important that in your description, you're trying to do some comparison. So you can see when we mention the energy needed, we say more energy is needed to break the strong covalent ionic bond compared to the weak van der Waals forces. So these are the words that showing that you are doing comparison. Okay, so try to avoid saying a common mistakes I have seen is that during melting, energy is needed to break the strong ionic bond in B. So B has a higher melting point. So that's not showing comparison between the two structure. Okay, so in order to show comparison, you have to mention more or less energy is needed and also which one is strong. So remember, we have ionic bond, covalent bond, metallic bond. They are strong bonds, and then we have intermolecular forces, the weak van der Waals forces. So that's all for Unit 9. If you have any questions, feel free to raise any questions in Google Classroom, and all the teachers, when we see the post, would like to answer your questions.